We're transitioning from particle to nuclear physics now, so we're going to talk about how the nucleus was discovered. This was, of course, through Rutherford's famous gold foil experiment, which I'm sure you remember from GCSE. We're just going to take a moment to acknowledge that Rutherford wasn't actually the one doing the experiments. He was on a research team with two people called Geiger and Marsden, and it was Geiger and Marsden who designed, built and carried out the experiments. Rutherford was the person who came up with a theory to explain the data that they collected. That was a huge achievement, and so he's quite rightly very famous for it. So here's a very simple diagram of their equipment. They fired alpha particles at gold foil. It wanted to be foil because it needed to be really thin, so as few atoms thick as possible. And it wanted to be gold because gold is famously unreactive, and you don't want these alpha particles reacting on their way through. You've then got this detecting screen round the outside, and this would flash where an alpha particle hit it. So you would see where the alpha particles ended up because you see a little flash on the screen. And what they were actually interested in was this angle here. So if this dotted line is straight on as far as the alpha particles are concerned, and let's say we've got an alpha particle comes in and ends up over there, then this angle here, the angle of deflection, that's the thing that they were measuring. Okay, at the time, many scientists thought that matter was quite homogeneous, so whatever was in there was all just sort of mixed up together and evenly spread around. And this was called the Plum pudding model of the atom, which you probably also remember from GCSE. Whether or not Rutherford thought that, we don't know. But he was certainly very surprised by, well, according to his version of events, very surprised by how dramatic the results of this experiment were. Because this is what happened. Virtually all of the alpha particles ended up there. So virtually everything that was fired at the gold foil managed to get straight through without hitting anything and ended up there on the screen. Now that was very surprising, the fact that it was virtually all of them, because that means that the gold foil has to be mostly empty space, or that wouldn't happen. So that was the first thing that was very dramatic. And the second thing was that some particles did get deflected. Some, were ending up all the way around here. But some even deflected by more than 90 degrees. So some of them hit the gold foil and actually bounced back this way. Now, to do that, they must have hit something very, very massive, much more massive than themselves. Now, it doesn't need to be charged, and Rutherford knew that. Rutherford knew that this did not prove that that it was a positive thing that they were hitting, but it had to be a very, very massive thing that they were hitting. And so that told us that the mass in here was concentrated in very small spots. So you had this very, very massive thing and then huge space, and then another very, very massive thing and then huge space. That is what must be in order to get the patterns that we see here. So what Rutherford said about this bouncing back, I'm going to change it slightly for a more modern audience, but he basically said it's like if you fired a cannonball at a piece of tissue paper and it bounced back at you. That's how surprising this was. Okay, so the conclusions of the experiment are these. This is the bit you need to know. So number one, most of the atom is empty space, and we know that because virtually all the alpha particles hit the screen there. And number two, most of the mass of an atom has to be concentrated in a very small space, and we know that because some particles bounced more than 90 degrees, that it were deflected by more than 90 degrees. Rutherford, this is not the extent of Rutherford's achievement here. Rutherford worked out the maths behind it. So he actually worked out the equation that tells you, based on the mass of the particle and thickness of the gold foil and all these sorts of things, he worked out the equation that would tell you the chances of a particle being deflected by what angle. So there's a lot more to his achievement here than what we need to know. But this is the bit we need to know. Okay, so here is an example question, and it's a little bit of a catch here. in that there's a log there. So have a go at this. Okay, so you just need to realise that having the log there doesn't make a difference to the overall pattern. Why have they put log n and not just n? It's because the difference between n here and n there is so big. It's like many orders of magnitude. Imagine if you had like a million up here and then you had like 0.00001 there. If you've got these huge differences in orders of magnitude, you take the log and then you get a pattern that you can work with. But it doesn't really matter here in the sense that we can still see that there were not very many particles deflected by this angle, and then there were more and more and more until when you get to not deflected at all, there were so many that they weren't even able to count. Right then, so for 3 marks, the first mark is for saying that most of the alpha particles went straight through without any deflection, and so most of the atom must be empty space. The second mark is for saying that some were deflected by more than 90 degrees, so there must be a nucleus, or there must be a concentration of matter inside the atom. And then the third mark is for an extra detail. You could have said the nucleus is very small compared to the atom, or you could have said that most of the mass is concentrated in the centre, or the nucleus is very dense, something like that.